So we looked at, talked about variable timers, single input timers, which is what we have, by the way, double input timers. Basically, the only difference between ours and a double input timer, which I think ours, Siemens, uh, Siemens. So basically, the only timers that I've seen that has double inputs, basically all they do, and Siemens had these type of timers, by the way. Sometimes we just connect the inputs together and it works the same as ours. But the way ours, like the 500, we have one timer input, and then and basically it's enable or start timing, but when it's able, it starts timing. Basically, the two inputs would have a start timing, and then it's got another one called enable. So if the enable is false and the start timing is true, it won't time. Or if the enable is true and the start timing is not true, the timer won't start timing. So this is, if you get into Siemens timers, these are the types that what we call the TIA portal. That's their newest programming application, and I'll give you all a look at that. Of course, RS Logic 500 uses single input timers. And then we have coil-based timers. So you might run into a PLC that's got a coil-based timer, where up at the top you might give it your address, and at the bottom you might give it your time, but it would be a coil type thing. Ours uses what we call a block type. Siemens TIA Portal, you got the option of either using this one or this type, whichever one you prefer. And why they left this one is the old Step 7. Their previous version of Step 7, the only timers you had available were coil type timers. When they came out with the TIA Portal, they added the block type timer. So what they kept both of them for, it was for a programmer that had been programming on Step 7 could move over. Off delay timers, on delay timers, are y'all okay on those? So an on delay timer starts timing when the rung becomes true. An off delay timer starts timing when the rung becomes false, right? And of course, we got the block type, so but they showed you. These are the three words, and I thought I corrected that, guys. I need to go back and do that. This guy, I don't know. So normally when we deal with registers are inside the microprocessor. If you look all through the data books and everything in fact, this is out of the actual data book for the 1100 or the programmer's manual. Uh, I don't say that, but they call it, yeah. So they call it element, word element. It's got three word elements. They don't use registers because registers are inside the processor. This book misuses that term all the time. So these are the three word registers. So every timer that we set up occupies three words of memory. And we can address them like that. So I could say, okay, I want the enable bit. Well, I could say T4, right, colon, and then we give it a timer number. Then I would put dot, I'd put a 0, and then I'd put slash, and I'd put 15. And that would address this bit right here. if I wanted to address the preset register, then I could say T4 colon 0. This would be my timer number. Then I would put dot 1. Now this is nice to know because what they've done is they've given these elements names. So instead of me having to know the enable bit is bit 15 in word 1, then I can come up here and I can say T4 colon, and this is the timer number, slash enable. So what they've done for us is they've given these bits in the status register, they're giving them names. So I don't have to know their address, right? You understand? So it's kind of like us giving our instructions, our addresses symbols. So the preset register, I can say T4, instead of putting 0, I'm going to put an X because that's the timer number. I can come over here and I can put dot because it's a whole word, and I can use PRE. And I can address the preset register without having to know it is word 1. You could have just as well said C4 colon X dot 1 because that's the preset register. This is the actual physical address. This is a logical address, which allows us to use names instead of numbers. So I can address the accumulator. I can say T4 timer number, colon timer number, and I can put dot ACC, I think. So we got names we can use instead of having to know this. We can use names instead of numbers. But they don't call them registers, they call them what? Elements. Because registers are inside of the microprocessor. And why I'm doing this is because these manuals are available. All your PLC manuals are available for free. Now, why do they give you the manuals? So normally when you buy the PLC, it'll come in a box and it might have a battery in there and that's about it. They don't give you the manuals anymore because they know you can get them what? You can get them free. You can download them online. And so I'm telling you this because you can look for this thing forever and you won't see the word register used in any of these manuals because the registers are inside the book. Retentive timers, non-retentive timers, these are true on all the PLCs I've programmed. So what's the difference in a retentive? So these guys reset when the run becomes what? On delay. These guys reset when the run becomes what? False. Retentive timers, they hold the time. So a retentive timer, you'll have to reset it with a reset instruction. And this is even true with RS Logic 5000. Let's see, move instruction. This is the one that we skip over. Move instruction is one of the most powerful instructions that you'll run into. What it does, it gives us the ability to move anything, any data file into any data file. So what does the preset register do for us? Well, I guarantee you that's going to be on test. What does the preset register do? I'm sorry. What does the preset element do? See, I'm doing the same thing. What does the preset element do? Well, this is the one I didn't see. So a timer, what's some things we need to, what's some of the things I need? It's a programmable timer. What's some of the things I need to be able to do with that timer? So we need to be able to set up the time, right? You understand? How long do we want it to time? So we got three registers in, we got three word elements in there. We got the status register, we've got the accumulator, and then we got the preset. So accumulator accumulates values, so that can't be it. So what we got is we got a preset register. Preset, that means that's where you preset the time, right? You understand? Yeah, but it's kind of weird in this timer. We got a multiplier that we use, which they call the time base. So what we have in these timers, by the way, RS Logic 5000 did away with the time base, but we're not taking RS Logic 5000 right now. So to calculate the time, you got to do two things. You got to take, if we're going to load the preset register, I keep saying register because the book says it goes. We're going to load the preset word, and then we're going to multiply it by a time base. This is going to be the timer time. Now the time bases available depends on the PLC. These are the time bases that are available on the MicroLogic 1100. The number of time-based multipliers is determined by the PLC model. I'd have to look at the 1000. I don't think it's got that. So the time base is not an element. It's not a word element. It's a multiplier that you select. So this one, the time is going to equal to the preset register times the time base. Now, if you want seconds, you're going to use a multiplier of 1. If you needed like, 10.4 seconds, then you would have to use a different time base. You might have to use this guy, right? You understand that? So if you want fractional seconds, you're going to have to use a multiplier besides 1. But if you're timing in seconds, then you would use a multiplier. If you're timing in in fractional seconds, you'll have to use another time base besides 1. If you're dealing with seconds, then you'll use I would use the multiplier of 1, even though the book don't do that. And the accumulator holds the accumulator bit. Time enable, we very seldom use that bit that's available, but it's there. So we can address this by timer 4. And of course, if you're on the 1100s, we could add more data files. And then I'd give it the timer number. And then I would put slash because this is a bit, and that I would be able to address the enable bit. These are the two that we use most often. This is a bit that is timer timing, and this gives you the address, and then timer done, this gives you the address. So given those bits names, we don't have to know what bits are status side. This is the way we address the two 16-bit words in there. One thing that I didn't deal is the largest number we can put in there is 32,767 because these are signed integers. So this is the largest thing that we can put in there. And this would be, if I use a multiplier of 1, this would be 32,767 seconds. Anybody know why we're limited to this? Yeah, because, well, it's assigned integers, what it is. So assigned integers, I can't set a timer up to I can't set a timer up to time a negative time, right? Understand that? So our negative numbers run from 32,768. These are negative numbers all the way up to a positive 32,767. So this is the only thing that's available on our timer for this PLC. So it uses a signed interval. So that's going to limit us, you know. I mean, good gracious, if I wanted a time for 24 hours, then I've got a problem. Because if I look at my calculator, then this is seconds. So 24 hours, if I wanted a time for 24 hours, then that's going to be times 60. That would be the number of minutes in 24 hours. And then times 60, that would be the number of seconds in 24 hours. So I can do this with one timer, and that's what we're going to look at in a minute. We can cascade the timer, so we can let timer one, after it's finished, it'll start timer two, and we can get just about any time that we need. By the way, Siemens supports hours, so it's pretty neat. So we looked at this, and like I said, the number of time-based multipliers depends on the PLC model. We looked at retentive timers, non-retentive timers, did some lab move instruction. I'm going to show y'all that. Here, what they're doing is, what we can do in the move instruction is we can take by the way, technically, when you read a book, these are called operands. So if you read the actual book, and it pops up, by the way, in this book, it usually pops up in PLC2. So these are the numbers that the instruction are operating on. And I'm not supposed to lean with a preposition on which, and I'm saying. These are called operands. So here what they're going to do is, and this is where you want to put it at. So if I close this switch right here, this is going to take this decimal number and it's going to store it in the preset register or the preset element for timer 0. So as I close that switch, this preset right here would go to 1000. If I close this switch right here, the preset would go to what? Can y'all see that? 1500. This should be the figure in your book, by the way, if you want to look at it a lot closer than what I've got. So this is in chapter 8. It should be the figure 8-2. So that operand, by the way, in PLC 2, take that class, we'll learn about different ways you can address operand. This is called immediate, by the way. So I've got a program. This is the PLC. So what I've got is I've got a program called RS Logic 500. Oh, I'm sorry, it's called Logic Pro. This is a simulator. It's run in a translator instead of a compiler, which is really neat because what I can do is I could verify a program before I actually put it into the PLC. So what this instruction right here is doing is I'm going to move, but look, I'm moving whatever's on input 3. Let's change these switches. Input in slot 3. I'm moving that whole word. So when I came in here and put it in, I said I:3. Then I put .0. So I'm getting the whole word, right? You understand that? And then I'm going to put this in the preset register of my timer 0, which is this guy right here. By the way, Logic Pro only allows a multiplier of 1.1. So we'll make this a little longer because it's only, so we'll make it 100, so that'll be 10 seconds. Okay. So what I'm going to do is I'm going to download this. I'm going to go online. I'm going to download this. And then I'll switch this to run. And this is, Logic Pro is a little different, but it's a pretty neat program. So right now over here on switch 3, now this is an input, and I'm just going to close some of these switches. Of course, the biggest number I can put in here is 32,706 days, so we'll be careful. Okay. And if you notice over here, if y'all can see this, I don't think I can make this bigger. Yeah. Every time I come over here and change this, let's stop working. Okay. Oh. That's what happened the other day. Okay, here we go. If I can't blow it up, guys, y'all just gonna have to. Oh, the mouse. So we'll just start counting over here. So you notice my operand here is changing. So this would be 0, this would be 1, this would be 2, this would be 3, this would be 4, 5, 6. So whatever I'm putting on my input over here, my operand right here is following that, right? Understand? So what I can do is I can come over here and put any number I want to. So that's 246. And what I'm going to do is I'm going to come over here and push this button right here. And what this is going to take this and move it into my preset. You'll see that? And then now when I start my timer timing, then it's going to time from there. So the move instruction is a very, very powerful instruction. What it does, it allows us to deal with what we refer to as variables. So a variable in a math formula is something that can do what? Change. So here I can take, with that move instruction, I can literally put anything in my preset register that I want to. So this allows us to actually deal with variables. Of course, all I gotta do is push this button, it loads it, preset goes to whatever I have set up on these switches, and then I can come over and start the timing. Now, the example in the book is technically variables, even though they're dealing with fixed numbers. So the one in the book is taking, if I close switch 1 on input 0, on module 0, it's going to put 1,000 into the preset. If I come up here and close switch 2, it's going to put 1,500 into the preset. So this is basically the same. So using the move instruction, what we could do is we could set up timers or even counters where we can determine the number. That makes sense? So I might be on a counter, I might be filling boxes that's got 12 in it, but I need to be able to switch to boxes that's got 24. So what we can do is we can use two move instructions and just switch it.
But you don't limit time on.
Yes. That's an on delay. It's timer. It's an on delay, and TOF is off delay, and then RTO is retentive on delay. So the retentive on delay, these guys reset automatically. On on delay, it runs through on off delay. A retentive timer, we have to reset it with a reset instruction, and we're going to use the reset instruction more than once. So we looked at our on delay timers, we looked at off delay timers, interlocking timers. What this does is give us the ability to generate a off and on, off and on, off and on. Let's see if we can find that one. Oh, I don't see. If I ever walk into plants, I'm gonna come up here. Let me save this first. So here's interlock timers, and I've got a start stop. I'm using a bit file. These B3s, these is one thing we can use those for what we call internal relay coils, right? Y'all understand that? You have questions on that? So the way this is set up is I have a start stop station. I'm using 0. Okay. So we'll download this, switch to run. Now what happens is this got scanned first. So this both these are true. Timer 1's going to take over. As soon as timer 1 starts, or timer 0 is going to take over. So let's watch this. So I'm going to press my start button, which is 1-1. I'm sorry. First of all, I got to make this a normally closed. So I'm using the example. This is a perfect example of I needed to use a normally closed, so I changed that to an examine closed instruction. So legally motor control gets that confused. I just touch my start, the thing starts slightly in. Notice timer 0 took over first, and then what's happening? They're just constantly doing what? Flip flop. And this would be my light indicating something's going on. And of course I've got it set up for a pretty good while. And you see these in plants all the time where they got lights that doing what? Flashing them. So this is one method we can use. They made it a little easier, but this is the one that's a bit. So these are called interlock timers. You're right, it acts kind of like a football screen. So I can change the time very easy. If I wanted the light to flash longer, I can come over here and put the light. I can reduce the time, I can make the on time less than the off time, I can make the on time more than the off time. All I have to do is just change the time on the timer. So these are interlock timers. Normally we use these things to flash things, to cause things to happen like that. And then the last thing we'll look at is what they call cascade timers, which hopefully you understand why we would need the cascade timer. This guy, we've only got 32,767 seconds is available to us, and that's seconds. So if I needed to go hours or something like that with a timer, I would have big problems. So the next thing, the last thing the book talks about is actually cascading timers. So cascade timers means we're going to start a timer, and then when it gets through, and these are supposed to be normally open contacts, by the way, the book is wrong. So the way it's set up, as soon as I downloaded this to the PLC and switched to run, these two guys right here would start timing. And so if you got your book, you need to change those over to normal open contact. So I come up here on this one, I close switch 0. This timer starts timing. And when it's done, this timer starts timing. And when it's done, this timer starts timing. Huh? Well, not until I disable it. These guys don't reset automatically. Now we could make it do it by making this one drop this out for just a second and come back. But there is different ways we can do that. So on mine, the actual program that I did in RS Logic 500 was where I've seen it used that before. Motors require a lot of current when you start them up. So one of the ratings that and it's like your car, so you're sitting at a red light and the light changes, you push the gas down, you push it down a pretty good ways to get your car in motion, right? And then when you get up to speed, what do you automatically do? You let it up, and you're going 60 miles an hour, and you're not using near the gas that was required to do what? Get that thing in motion from the stop. So there's a rating on a motor. It's called the full load current, and it's usually rated in amps. And this rating of the motor is called the full load current. So if you ever look at the nameplate on a motor, it'll be on there and it'll be rated in amps. And over here it might say 10 amps. Now, what this is what the motor should pull when it's running at speed under its load. So if you had a 5 horsepower motor, then if you loaded it with 5 horsepower, right, you understand, then it would pull 10 amps. That makes sense?
But to start it, that's FLA, right?
Yeah, this is full load current. If you ran it overloaded, it would pull more, but then it might have a chance of stalling, which is not good on a motor. But when you start it, it's got a code on there that you use to multiply the full load current to give you the start current. Rule of thumb is, if you don't know that, it's 6 to 8 times.
What's the symbol they use? There's FLA and then there's the amplitude, the start the motor.
It's a code. I can't remember what it's called, but it's like an A, B, C, D. It's a letter. And then you have to look it up on a chart, and then it tells you the multiply. That's a really good question. I need to know that because I think it don't come to my mind right now. So technically, this motor right here can pull. When I try to start it, it can pull 60 to 80 amps. Just get it started.
Yeah.
Well, the problem is I've got 10 motors out there, and I start them all at the same time. Not good, right? That'd be a ton. So there's a technique we use where we sequence start motors. So we'll start one and maybe 10 seconds later when we start. So this is a really, really good example of cascade. Well, the cascade timers to exceed this 32,767 limit that we're doing. So I can let this timer start that timer, right? You understand? And we can get just about any time we want to. The example I came up here was I had, I think 4 motors. Oops, I need to take it out of run. I'm gonna upload this and then cascade timer. So on this one, I got 3 motors. I'm starting, motor 1's going to start instantly, and then after 15 seconds, motor 2 should start, and after that, motor 3, motor 4. But what I've done is I've cascaded the timer. So notice, as soon as I hit my start button, motor 1's going to come in. When motor 1 comes in, I'm going to take that output, and I'm going to enable this timer. This timer times for 15 seconds. Nothing happens because it's then over here, when it times out, this timer starts timing, but I'm also starting motor 2. And when this guy times out, this closes, I'm going to start motor 3. And then after this guy times out, I'm going to start motor 4. So what we should see happen is this guy should come on, this guy should come on, this guy should come on. So here we're sequence starting for 4 motors. So cascade timers, we can use these for sequencers. So we can say after this time this happens, after this time this happens, after this time this happens. So let's download it. And of course, I'm using input 3 here, so I need to change this to normally closed. And I'm going to change this to normally open. And then we'll switch. Okay. So I can come over and just hit my start button, and we should see motor 1 come. This is motor 1, motor 2, motor 3, motor 4. We should see this guy start instantly. I'm using 3. So motor 1 started instantly. Then after what I got, 115 times motor 1 started 15 seconds, then motor 2 should start, and motor 3 should start. So we use cascade timers to exceed the 32,768, right? So I could set this to 32,767. Then I could set this to 32,767. Then when this is true, it starts this timer, and then basically I would trigger whatever I wanted to trigger after the last time. And usually we wouldn't use 32,760. We usually use even numbers to make them easier to figure. So there's 4 motors. Sequence started 15 seconds after each motor. So this is what we use cascade timers. What does it do is it allows us to exceed the right, just 32,767 seconds that we're limited to on these guys. And it also allows us to sequence start something. Here I set them the same. They don't even have to be set the same, right? You understand? And then of course, if they have to stop, they should all stop at the same time. So you'll see how I did that. I took this B3 file, this B3 bit, which is an internal coil. I didn't want to sacrifice one of my outputs, even though I got a lot of outputs on the simulator. This is we call these internal coils because they don't need to generate an output, but they act just like a real coil, right? I'll play around with that too. So that's it on timers. What do you need to know? Well, first of all, you need to know how to address the timer. The default data file is P4. Now, if you're on the 1000, that's all you got. But we can set up more timer data files. Each data file, each timer requires 3 words of memory. Right? So we have the preset register. This holds it's not the time, it's we use to calculate the time, right? So on these, how do you come up with the time. You take the preset register, then you multiply it by the time base. So Logic Pro, it's only got one time base available, and that's 0.1. But we come back and look at these other timers. This guy here's got 3 time bases available, and this is a multiplier. So to come up with the time, you take the what? You take the preset you take the preset word, you multiply it by the time base. The accumulator holds the what? It holds the time that you're at, right? So it actually updates as the timer times up or times down. And you need to know how to address these registers. So how do we address the done bit? So the done bit, we start off with T4. We can't do anything about this right now. Now, of course, and why we have to specify all this is so inputs and outputs, we don't have to specify the data file number because those are set by hardware, right? Understand? But on MicroLogic 1100, I can create a T9, and then we would have 256 more timers we could have. So this specifies timers. This is a data file number. Then we come over here and then we put a timer number. And you don't have to go in sequence, guys. I mean, all this is going to be is just going to be a number between 0 and 255. Then if I wanted to just enable the done bit, I would put a backslash. I'd put a slash. It's not a backslash. And then I would put what? Done. D in done. Or I would put what? TT. What would that be? Timer timing. Or I would put EN timer enable. We don't use this one very often. If I wanted to address the accumulator, I'd say T4 colon on our lab. Then I would put the timer number. Then I would put a dot because the accumulator is a 16, it's a word. And then I would put ACC. If I wanted to address the preset, then I would put timer number PRE. And this is the way, so this says I'm addressing a whole what? Word. The timer is just going to be T4 when I slide the timer address. And then this is going to be the timer number. That makes sense? Everybody okay? So I'd come over here and I would call this T4 colon 3. And then I'm through. No slashes, no dashes because we're actually addressing 3 words. So we specify a timer number, and then that specifies which 3 words we're doing. Oh, y'all still writing that down? Hey, sorry. Now, if you knew the word number, if you knew the bit number, you could use that. But what they're allowing us to do, since we use these so often, they're giving these words, these word elements, they're giving them names. We okay? Okay. So counters, very, very important. Timers, you see these all over the place. If you understand timers, you'll understand counters a little better because the registers are basically, not the registers, the data elements or word elements of the time. So counter output instructions, these are output instructions, some of the time instructions displayed in block format or core format. Our Logic 500 uses block format. So we could have single input or double two input, all ours are single input. Series program logic code uses one input for both enable and count. Addresses can be, for ours, for this class, is going to be anywhere from C5:0 up to C5:255. And you do not have to go in sequence. Some Alabama PLCs allow data files 9 through 255 to be used as counters. But actually, we give these numbers and it seems like a lot. So timer counters would be, I could have up to 256, but each one of them is going to require three words of memory. So what actually determines the number that you can have, even though these are available, what actually determines the number you'll end up being able to put into your PLC is how much memory is actually in your PLC itself. Have two basic types of counters. Well, actually, we have three. RS Logic only supports two. We have an up counter, so these will start at a number and count up. Then we have down counters. These will start at a number and count down. And then some PLCs provide what we call up-down counters. RS Logic 500 does not support this. Siemens does. RS Logic 5000, I'm not actually sure if they got one of these. So here are our registers. Not our registers. Here's our word elements, guys. Use the whole, so we got one called preset, C5:. So the counters, when we set up a counter, we'll assign it an address. We'll say C5:, and then we'll give it a number when we program it. If I want to address the preset register, use to hold the preset count number. So this is what we want to count to, not what we're counting from, what we're going to count to. So if I wanted to count to 5, then I would put 5 in the preset register. The accumulator holds the accumulated count, which now is not going to mean much, but if you take PLC 2, we'll learn about an instruction called compare, where we could actually look at the accumulator and cause things to happen. If we got a count of 15, we could cause things to happen on a count of 4, count of 6, and that kind of stuff. So we're not really going to be able to use this, or we will. Status word holds flag bits that are used by the PLC to keep track of the operation of the counter. And this is going to be C5:/, so I need to do that. And then we'll give it, we're going to put it the name of the bit. So I need to correct my PowerPoint there. In fact, while I'm thinking about it, I need to go ahead and do it. So here's the word element. So we have word 0, here's your flag. So in a status register, we call it a flag because it's a bit that's going to set or clear depending on what it looks at. So it'd be like raising a flag, right? So this is another name they give these bits in a status register. They call them flags. Here's my preset register. So this is where we're going to put what we want to count to. accumulator value is gonna hold its current count, right? And then we have a count up enable, count down enable. We have a counter done, which we're going to use a lot. And then we have what we call overflow bit. So the maximum an up counter can count to, the maximum it can count to is 32,767. The maximum a down counter can count is a minus 32,768. What do you think will happen if you make it count up to the 32, past the 32,767? It will count. So what happens, this bit right here, so we got 16 bits. And then the 16th bit, this is what we call the sign bit. So a 0 indicates it's positive, and a 1 indicates it's negative. So this would be 37,767. Sorry. That'll be 32,767. I count the 1. This would go to 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. And it thinks it's negative. So it would actually flip over to, that's by the way, that's a minus 32,768. We don't give it why. So what happens is we need to have an indication, and we'll see this. RSLogic Pro won't do that. So I've got this thing I'm going to show y'all in a minute where I actually count. I load the thing with a big old number and I count, and you'll see the thing go negative. So instead of going to a positive 32,768, it flips over to what? Negative. Well, we have to have an indication of that. So an overflow would indicate we've gone past 32, we got to count greater than 32,712. An underflow means I've got a count of less than a minus 32,768. If I try to count one past that, the number will go positive. I'm looking for RSLogic video. There it is. So here it is right here. Let me, I think I got it running. So here I've loaded, and I can blow this up. This is actually on the PLC because it don't work right. It don't work right on Logic Pro. Logic Pro. So right now I've got 32,769. And what I'm going to do is I'm going to just come over and hit switch 0. And notice it's counting. 32,764, 5, 6, 60. Here we go. 32,767. Watch what happens to the sign. What it is. Went negative. And notice my overflow bit changed. So this would give an indication that I could monitor that overflow bit inside the status word and know when this happened. And what I'd probably do is I would start another count again. Now watch what happens. Right now I got 32,768. I did this on purpose. Now watch what happens when I do one more count. Right now it's negative. And what did it do? Went positive, right? Yeah. Of course, now what I got is I got an underflow bit indicating that my down counter has exceeded 32,768. So that's something on this guy that you got to keep in mind, right? Y'all understand why? Because that could cause a big problem. So that's what the underflow and overflow. By the way, these are move instructions, and this is where I'm getting these numbers into the accumulator. I'm not, the presets are up here. So the presets I put in there. But using a move instruction, I can move anything, any data word into any data word, any data file. So notice when I come down here and activate this move instruction, which is switch one, and watch what happens to my accumulator. So that move instruction is very, 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 very powerful. You can move anything you want to into any data word. So you could set up output bits to whatever you wanted them to be. So there's underflow and overflow. This is when we see the rain, so y'all need to know that. Count up bit, true when the up counter is counting. Count down is true when the down counter is counting. Overflow, we know what that means. True when the counter, up counter exceeds a positive 32,767. You go one more count, then thing does what? Changes sign. The underflow bit, true when the down counter's accumulator exceeds minus 32,767. By the way, these are all software counters, so these are all built into the program. So there's a line of code, machine code that you don't see that executes an up. One advantage we have is hardware, electronic circuits are always faster than programs. So what was happening, we were exceeding the count that the counters inside these software counters could keep up with. So what they did is they added counters back into the hardware of the PLC. We call them high-speed counters. These are actual hardware counters. It's all PLC support. And so these run, once you set them up, they run, and what you do is you read them at a certain amount of time with your program. For up counters, once the value of the count accumulator matches or exceeds the preset value, the done bit is set. The counter will continue counting. So it's not like a timer. So a timer, when it hits its preset value, it just stops. A counter will continue counting. And to clear out the accumulator, we have to use a reset. Same one, by the way, that we use to reset or reset. The move instruction can always also be used to set the accumulator preset to any value besides, which is what I did on my program. So these are your preset register. Notice I marked it. I put a thing up there. And they call them registers, but they're not. They're words. Over here, by the way, they call them negative time. This has nothing to do with counter. But each thing is wrong. So undoubtedly, the guy, I don't know what it is. The counter done. What did you say? Set count up, count down, count up, count down, timer done, overflow, underflow. So I don't know where I got that at, guys. What am I missing? Count up, count down, overflow, under, let's see. Under, and I've got UA out there, not UA. Done, yeah, thank you. Don't ask me how I came up with that. This UN might be wrong too. It is. So done. So if you got your book and you need to mark these out, well, these are all timers. This is, I don't know, I don't have the figure number on this. Anybody find it? This is in chapter 9. In chapter 9. Okay, guys, let's take a 10-minute break. Anybody that came in late. So, I've got an up counter, which makes sense. The down counter, you're going to have to think about. So I have an up counter, I'm calling it 250. When you come up with a counter address, that's actually address in 3 words. There's no slashes, no dashes, or anything like that. Somebody in this class is going to do this. Now notice this one, since I'm starting from 0, I loaded this with a positive 1. So right now the done bit is set. I'm sorry, the done bit is clear. Here on my down counter, since my accumulator is 0, I had to load this with a negative number because I'm counting from 0, right? You understand that? Now notice here, if your accumulator is greater than your preset, then the done bit starts off 1. So my accumulator, so this Arch Logic 5000, these are exactly the same way. So I'm going to start counting on my up counter. I've got this hooked up to switch 0. So count. And now it's going to come up, done bit set. Everybody understand? So I'm turning on one of my outputs. This output started off true. And I'm going to count counter 1, or counter 1, -1, -2, -3, -4, -5, -6, -7, -8, -9, -10, -11. So you got on your down counter, you have to be 1 more past your preset date. It matches. Now the problem is, I'm going to come up here on counter 0. Counter 0, what's going to happen if I give it enough count? What's going to happen if I give it another count? What's going to happen when I give it another count? Keep what? Keep counting? That would be awful if I made a mistake and put the wrong preset date in there and I lost count of what I wanted to go to. Right, it still says it's done, right? And the same thing happens with the down count. It's counting down. So how do I get this thing to go back to 0? reset. Same one. You notice inside your group, I've got Onblay, if y'all can see it. I got tall off today. I got retentive kind of. I got CPU count up. I got CPD count down, and then I've got this reset. So this reset applies to both your counters and your timers, your retentive timers. Excuse me. So what I do, I've got a reset on switch 3. This is going to reset timer 0. So I give it the same address, C5:0. And then this right here is going to see reset counter C5:1. So if I come over and hit switch 2, both the counters reset. So we looked at the overflow and underflow, right? So if I let this counter count up to greater than 32,767, it's going to change sign, right? If I make this guy count less than minus 32,768, it's going to change sign. So we got an indication of that. So we could start another counter counting, right? You understand? So if I've got an overflow, then I could enable another counter and get greater than 32,768. In fact, we usually count in 10. You know, like instead of it's a weird number. If you don't understand binary, 32,767. So I might reset it on 20,000 or 30,000, and just go ahead and stop it and start another counter before it even has a chance to do what. Of course, y'all don't know how to do it now because we don't know the pairs. Another option I have on this guy. Let me change the program just a little bit. So I'm gonna go offline. And then on the down counter, let's add another rung in here. Oh, I am offline. So user, and then we'll add another rung. Okay. And then we'll make another switch. Then I'll come over here. Move instruction. Oh, I'm gonna have to do this with Logic Pro. We don't have enough inputs on here. So what I've done is I'm using a move instruction, and I'm putting 10, and it did it in hex, by the way, I don't know why. For some reason, why it's so, I put an A using the 10, but notice it's got the little H out there, which indicates hex. So what I'm gonna do, this is a little different, to make it a little more, of course your lab will, do this. And this is the power of that move instruction. So we'll go to run. So what I'm gonna do when I hit switch 0, I put 10 into the accumulator. So now when I come over here and hit switch 1, it's counting down from 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and we got to go one pass -1. So here, that's a little different. In your lab book, they show you how to load the preset. And if you load the preset, you got to load it with a negative number. If I load the accumulator, I can load it with a positive number, right? Preset, you have to put for a down counter, you have to put a negative. If you put a positive number, what would happen if you put a positive number in there? You would have to count all the way around to 0 and then come back around. Yeah, so you'd be here forever. So that's why you need to load it with a negative number. But if you use the move instruction, you can put a positive number in the accumulator and the preset register is 0 and it will count down, but you still got to go past 1. So all the ones in the textbook and the ones that are on the test are going to let you set this thing up. So on ours, negative numbers in the preset, you got to go one more negative because the done bit's too clear. So the done bit starts, so on a down counter, the done bit starts off set, and you got to go one more negative then for it to do what? For it to reset or clear. And I think that's it for counters, guys. Count up instruction, logic diagram user count up. By the way, we can cascade timers. Y'all understand what that means, right? So I could have an up counter, and when it's done, it would enable another counter, right? And so that way we can exceed the range. So let's do that on the PLC. So I'm gonna not save this. I'm gonna delete this run, and then we'll start at go new, right? And no. First thing we have to do is select the CPU. And I've got 1100D. Okay. And then we'll come up here and we'll put a counter instruction. Well, first of all, we'll insert a run. Oh wait. So this is your palette. So this stays up all the time. So what you don't have to do is you don't have to go to here. So I'm going to insert a row. Then I'm going to insert a normally open contact. Then I'm going to insert a counter. And they're in alphabetical order, an up counter. And then we'll come down here and put another rung. Then I'm going to put open contact. Then I'm going to put another up counter. And I'll close my palette out because it's in the way. Here we'll assign this to input 0/0. We'll call it counter 1. We're just going to cascade counters. We're not going to use the done. I'm just going to show you how this would work. Then over here we'll assign this to input :0 :0 0/1. And we'll call this It didn't take my one up there. But counted two. And then, of course, I got to give it an address. So we'll call it C5 colon 10. So you don't have to go in order, right? You understand that? And then preset, I'll preset it to 10 just because all we're trying to do. So I got this one wrong. What I'm going to do on this one, I'm going to use counter 5 colon 10. And over here, I'm going to use the run bid. And this right here, we'll call it counter C5 colon 34. So you don't have to go in sequence of those. So we'll check it for errors to see if we got a syntax error. We don't. So we'll download it to the PLC. Mine's on the wrong side, though. And we'll give it a name. I've already got a cascade counter in there. Like I said, I always thought this was weird that it don't ask you for a name of the program until you do what? Until you download it or save it. If you save it, you'll do that. Switch it to the rub mode. Here though, we got a little problem. Let me go offline. Nobody caught me on that. We need to put a preset count into this timer, or it'll be done enough to start off with. No, we're still not through. I'm back offline. I still am offline. We're trying to cascade them. Someone come over here and find this too. Still not right. 10, done. No errors. What we're trying to do is we're trying to cascade them, right? So the first counter, we'll count it with switch 0. Oh, sorry. Let me do something right in there. So we wanted to cascade, but I'm getting too stuff. Colon 0. 10. There we go. I don't know why I kept switching. Okay, so now we can go. So I'm using the same input, and I switched over to another input, but I wanted y'all to see how we cascade timers. So we go back to the run mode, and then I'm gonna hit switch 0. And of course, counter 1 starts counting. Counter 1 starts counting. This is flashing, but it's waiting on this other one to do what? Get done. And then when it hits 10, then the next counter starts counting. So this is the way we can cascade counters if what? If we needed to exceed this 32,767. Or if we needed different counts, we can move the move instruction to set the accumulator or the preset register to any preset value that we want to kind of like the timer. But this is the way we can cascade them. Are we okay? Make sense? So yeah, so it seems like that's a big deal, just 37,000, but what we're, is 32,767, and it is for RSLOG 500. Of course, this is the thing that they took care of on newer PLCs. So newer PLCs, we can specify counters with 64-bit sign numbers, double words, which probably will count more than any company would ever need. So, but this is something we'll have to watch out for. Another thing is this down counter. Normally we load it with a negative number, and you have to go one past the number before the done resets. So the down counter, the done bit starts off set, and you got to go one past. And I think that's it for counters. Any questions on counters? Cascade counters. We don't use cross coupled counters. Countdown instruction. Count up. Done coiled is energized when the contents of the accumulator. So when the contents of the accumulator word element is equal or exceeds the contents of the preset. Countdown instruction. Done coiled de-energizes. So it starts off energizing when the contents of the accumulator word element becomes more negative than the preset one. This is the way we get that. And then we got the overflow bit. So the overflow indicates when an up counter gets past 32,767, right? Or a down counter, we call that the underflow bit. It gives us an indication if a down counter ever goes past a negative 32,760. And this just talks about different things that they do, right? So, any questions on counters? Speak now, forever hold your peace, right?